Every time you buy a new phone, you're bombarded with marketing about the blazing fast speeds of 5G or the upcoming power of 6G. But for most of what we do every day, 4G works perfectly fine. This raises a question. Why do telecom companies spend billions overhauling the global network every 10 years? To understand that, we have to look back to a time when making a phone call meant you were physically tethered to a building. Before the 1980s, if you wanted to talk to someone, you were using a cable plugged into a home, an office, or occasionally a heavy, expensive setup installed directly inside a car. That changed in the early 1980s with 1G. This first generation of mobile networks converted your voice into analog radio signals and beamed them through the air. You could finally walk and talk at the same time, provided you had the arm strength to carry around this massive, brick-like design. But this analog technology was incredibly inefficient. Continuously converting a voice into radio signals drained the battery so heavily that you could only talk for about 20 minutes before the phone died. 1G also presented a security nightmare. Because it used raw radio waves broadcasting through the air without encryption, anyone with a basic radio scanner could tack right into your frequency and listen to your entire private conversation. While 1G proved wireless calling was possible, these physical and security flaws made it unsustainable. It sparked a cycle where every subsequent network would be built specifically to patch the glaring problems of the generation that came before it. In the early 1990s, 2G solved the security problem by switching the network from analog radio waves to encrypted digital data. Moving to digital data created a useful byproduct. Because phones could now process small packets of data, users could send SMS text messages by clinking away on physical number pads. It also allowed for the very first versions of mobile internet access. However, 2G went agonizingly slow, topping out at around 200 kilobits per second. The high latency made clicking a link feel unresponsive, and URLs had to be typed letter by letter, making real web browsing practically impossible. 3G arrived in the early 2000s as the first network explicitly built for the internet, eventually pushing speeds up to 10 megabits per second. This speed unlocked new capabilities, like streaming early YouTube videos or making basic video calls on the go. But 3G was not designed for mass simultaneous usage. As the smartphone boom began, millions of people trying to pull data at the same time caused the network to buckle, leaving users stuck with constant buffering and unstable connections. 3G proved that people wanted the mobile web, but it exposed the fact that the underlying infrastructure lacked the capacity to deliver it reliably. To fix this capacity bottleneck, 4G LTE launched around 2010. By increasing stability and pushing speeds up to 300 megabits per second, 4G provided the bandwidth needed to prevent the mobile web from collapsing. This jump in speed actually changed the physical design of our phones. Because 4G could handle complex data reliably, manufacturers began removing physical buttons to make room for the large touchscreens needed for sophisticated apps. High-resolution video conferencing and gesture-based maps became standard, requiring an interface that could handle scrolling and zooming in ways a tiny keypad couldn't. Even with its high capacity, 4G still has limits. When tens of thousands of users crowd into a single stadium or city center, the network becomes overloaded and speeds drop significantly for everyone. 5G addresses this overcrowding by maintaining high-speed stability even in the densest urban environments. Beyond raw speed, 5G offers low latency. This is the near-instantaneous response time between sending a command and the network reacting, usually just 15 to 30 milliseconds in the real world. This instant response is vital for specialized tasks, like disaster rescue. Pilots can control a drone and view its live camera feed with virtually no delay, allowing them to make precise, split-second decisions in the field. 5G provides a high-capacity data pipeline while ensuring the near-zero lag required for real-time control. Looking ahead to 2030, researchers are currently developing 6G. In laboratory conditions, these networks are already reaching speeds of a full terabit per second. 6G centers on structural intelligence. These networks will use integrated AI to predict data demands before they happen and automatically reroute heavy traffic to keep the system balanced for millions of users at once. This level of performance is tailored for advanced machine automation and complex scientific grids rather than everyday phone apps. For most of us, 4G and 5G are already perfectly optimized for our daily lives. Messaging, social media, and video streaming simply don't require the extreme speeds found in the lab. The cycle of network innovation will continue to push technical boundaries, but for the average user, the technology has caught up to our needs. You can safely ignore the hype for the next G. The speed you have in your pocket today is already more than enough.